continue. So hello everybody. So today we are at the very last of the training course on stochastic methods in finance, and what I have told you yesterday. So yesterday I've made a brief introduction to credit risk. So I've told you what credit risk is from the point of the mathematical point of view, how to deal with that. And I think I've exhausted the topic of individual credit risk linked to individual entity. And my general conclusion was that credit risk, so pricing credit derivatives, instruments exposed to the risk of credit spreads, doesn't differ too much or doesn't differ at all from the pricing of interest rate derivatives. So everything you know on interest rate derivatives applies to individual credit risk. What means that you may use all the tricks, including those tricks that in principle you should not use, namely interest rates may be negative, but credit spreads should be not, because probability rarely exceeds 1. But in practice we do. But dealing with individual names in the modeling of credit risk is not the most important part of the theory.
Dariusz.
Yes?
Are you sharing the slides?
Oh, lady, sorry. I should click somewhere. Okay, sorry. I was sure I did something wrong. Now, I should find the button to click to share the slides. Wow. And oh yes, of course. Okay. Now it's okay. Now it's okay. I was sure I will spoil something.
No, it's okay. Perfect.
So, but you know, one little error. At the beginning of the last day, so that's not a massive flaw. Okay, so what is important in the area of credit risk modeling? Default correlation. So now let's forget about mathematics and take the notion correlation in common sense meaning. So what is correlation? It's mutual dependence of one phenomenon from from another. So in the case of defaults, this is the situation, then probability, again, probability in the common sense meaning of having two defaults in a short time is larger than probability of having two independent defaults in a short time. Yes, because for independent defaults, we've got a principle of multiplication of probability. But these defaults may be more condensated. And that is something that may be painful for us. So take an instance of a bank which got many credits. And of course, we are prepared that some credits default. But when they default in a cascade, so not only one credit defaults, but a number of them, that may lead to serious problems, even to insolvency of a bank. And trading credit products with a counterparty poses a natural question of credit correlation of the traded product and this counterparty. So an example, an Italian bank had a lot in its portfolio, had a lot of Italian bonds. And it was a problem to price, how to price them. So should we price these bonds as they were held by, say, an American or a German bank? I'm not sure, because probability of default of a big Italian credit institution and Italian state at the same time is much larger than probability of default of big Italian institution and America or Germany, yes? So there is sense of dealing with correlations in the world. And now a question appears. Now let us pass to mathematics. So when we mathematicians, especially probabilists, hear the word correlation, what bell rings in our head? Gaussian correlation, of course. So I don't know if this your case, my case, it is for sure. So if we take two Gaussian random variables, there is a complete and not sophisticated theory how to correlate them. So we've got a representation that on one hand, these two Gaussian variables may be completely correlated, so coincide, or one being a linear function of the other, or independent. And there is an obvious representation of that phenomenon. Do you have any questions about that? So okay, you don't. Good. On one hand, we've got co-monotonicity. So for the correlation parameter equal 1, correlation parameter just called correlation. And for correlation parameter equals 0, we've got independence. So far, so good. But now, defaults are not Gaussian variables. Yes, because the positive random variables, and Gaussian variables might be negative as well. And the possibility of negativity is included into the Gaussian distribution. So we can't do any dirty tricks. So how to construct correlation for random variables, so namely positive random variables for default times. And so probably the first idea, the most obvious, is to transform the actual distribution of the default time to the Gaussian distribution. So we take default times, so positive random variables with some distribution. F's are their distributions, and phi is the distribution of the normal distribution. So I think known to all of us. And then just manipulate, transform.
Sorry, Dariusz, there is a question.
Yes.
If as you told us, we use a local or stochastic volatility for underlying, what kind of correlations do you take into account? Is it tractable?
Perfect question. Perfect question. Of course, I will arrive to answer that. But that question, which sounds very obvious, hasn't got a satisfactory answer. So I will tell you, of course, about the answer I believe in, but it's not a common view. So most people will, even respected probability or finance professor will answer, I don't know. So that's the situation. So credit risk modeling is something what I like. We don't have lengthy formulae, but we've got a lot to think. So it's a conceptual theory. Yes, but let's keep in memory this question. Of course, so far I'm just dealing with positive random variables without that property of measurability with respect to a sigma field, so not real stopping times, and I'm in trouble. So when I pass to real stopping time, the trouble will be serious. Okay, so but back to our simple algebra called Copulae. So when we take this guy, x is of course normal variable, standard normal variable. When we take function phi over that, we've got uniform distribution on the interval from 0 to 1, and taking phi inverted phi of that, we'll get this distribution of no, it's not phi, but f. I forgot names of letters. We'll get the distribution of f. So that's all algebra. You may make some exercises at home. And Okay, so that's where the correlation between those random variables is more complex. But in the most cases, we just want to correlate. So this is the way how Sharpe thought of financial markets, that there is one driving factor driving the whole market, and individual idiosyncratic parameters of all the names. So here we've got that situation that we've got one systematic factor driving all the defaults and many independent individual factors, and we correlate them. So in the situation where alpha is equal, alpha 1 is equal 1, we've got total correlation. So we've got only one driving factor of defaults. So defaults are co-monotonic. First default determines the next defaults. And in the opposite situation, when alphas are equal 0, we've got independent defaults. Yes, so this is that picture. On one hand, we've got independent defaults, on the other, co-monotonic. And this trick is called Gaussian copula. Why copula? That's got to do a lot to do with the word you are thinking of and the word couple in English, because this is linking two entities. Yes, because copula links one point here with another here, yeah? And this is a line like that. And this is exactly what we do. We link systematic factor here with idiosyncratic factor here, and impose various levels of correlations. And there will be one theorem without proof. So the proof is lengthy and there is a lot of calculations. So believe me, it is like that. The formula belongs to Oldřich Vasíček. There's large full approximations. What is large full approximation? When in our portfolio, we've got a large number, so many entities with the same default distribution. So we don't distinguish them, but we would like to impose some level of correlation between them. So on one hand, independent, on the other hand, co-monotonic. So this is what I have told you is written here in mathematical terms. And when we, n is the function counting default, and when the asymptotic formula for this function is that. So F is, I remind you, the distribution of all defaults, and phi is the standard normal distribution. And you've got this not much sophisticated formula, not painful. Who invented or smuggled from insurance mathematics? It was David Lee, who did it some 20 years back. So he introduced the Gaussian copula to finance. And poor David was blamed for the financial crisis of the 2008. Was he guilty? How do you think? What's the mathematician's responsibility for the world? Okay, so we won't judge David, but again, back to Nicolas Gomez-Davila, we should not replace thinking but by mathematics. So understanding, and this is what the market participants, say 10 years ago did, not 10, 15, something 15 years ago, did. They just believed a mathematical formula, skipping common sense. Of course, common sense goes perfectly together with mathematics. Maybe without mathematics is not sufficient, but mathematics without common sense is misleading as well. And of course, that trick with Gaussian copula was repeated with other functions than the standard normal distribution, because everything is about interpolation between comonotonicity. Horrible word. I would like to hear an Englishman saying that. So comonotonic defaults and independent defaults. So we may, of course, construct some other functions with that interpolation. So some 15 years ago, it was a perfect way to write a paper, write a quoted paper, well received, and so on. And these copulae have names. So Gamble, Clayton, Student T, Marshall, Olkin. That one is especially interesting. I will tell you a bit more. Marshall Olkin copula. I'm not going to give you formulae for these functions. Phi I. You might find it in many books. I think it's useless. It's purely academic. And I don't know. It's not a very good mathematics. It's analysis one mathematics. Okay. So again, this picture. What is that all about? So to construct a function interpolating the dependence level from independent to co-monotonic. Yeah. And here you may read the critique of copulas by an eminent expert in this field. Okay, so this is bitter and sarcastic, but the first sentence is especially important. So stochastic processes is, stochastic analysis is a field of knowledge, and copulas are just tricks. So neither interesting from the practical point of view, nor from the academic. So apologies to all the people who choose copulas. But, okay, I said it's not interesting from practical point of view, but that's not true because the Gaussian copula is still used in the industry. It's a pity, but it's practice. So it's something we learn about industry. At the end of the lecture, I will talk about intellectual customs. Okay. Third idea is you probably already forgot about structural models of default. But this is quite a good way to deal with dependence, deal with correlation. So we built several models, structural models of entities, level of assets, for instance, or level, and just correlate it. And see what comes out. You never get closed formulae in this approach. Never. So I didn't. It's just numerical mathematics. But okay, I will not discuss how good this approach is, but there is a strong danger of overfitting because structural models got many parameters. We don't control the number of parameters. Okay, so a model based on Marshall-Olkin copula, a bit reformulated, and okay, okay, it's based on Marshall-Olkin, but not much directly, but we've got still the same philosophy as here. So we would like to build an interpolation between independent defaults and co-monotonic defaults. Why Marshall-Olkin copula is the best? Because this copula is linked to Poisson distribution, which is natural distribution. Okay, maybe not Poisson distribution, but exponential distribution. And exponential distribution is a natural distribution on the positive line. So like Gaussian distribution is the most natural one on the whole line. So on this positive part of that, we deal with exponential distributions. So we've got all the analytics. So what we would like to do, we try when having distribution of default time, Fi, we deal that into two parts. Into this idiosyncratic part. No, the opposite. No, okay. All right. Idiosyncratic part, H, and systematic G. And they are mutually linked by this formula. You will see later one. And we construct independent random variables some way, Y with the distribution H and Z with the distribution G, but G is around one systematic default factor.
Sorry, Dariusz, I have another question.
Yes?
Is it possible to include more than one systemic factor for pricing, or it is more for rating or for ratings?
The answer is positive. Yes, we may introduce as many factors both in the Gaussian copula, in other copulas, as many factors as we want, but for the purpose of the lecture, I reduced to one factor, because if you had more factors on the screen, you wouldn't be able to read anything, because the notation would be very complex, and the concept doesn't change. So let us think that way. I will tell you about one factor, but and you will say to yourself, it's identical, it's exactly the same with more factors. So that is just to simplify notation and the presentation. Everything is reduced to one factor. So I think Sharp did exactly the same. So he presented his theory with one factor and adding at the very end, and if you have more factors, is exactly the same. Okay, so how the default time is constructed? So the default is the first of two defaults of every entity. Default of every entity is first of two defaults: idiosyncratic one or systematic one. And here we've got a bit of simple algebra to prove that distribution of tau I is exactly Fi. So what was now our initial assumptions. So using the property for expectation of multiplication of two independent random variables. Okay, so what we have in this here, I remind you from the very beginning of the lecture that distributions, default distributions, are represented by hazard rates. And for this model, we've got a nice hazard rate representation. So hazard rate for F, for the distribution of the default, is just a sum of the idiosyncratic hazard rate and systematic hazard rate. So this is intuitive. Unlike Gaussian copula, which was strongly counterintuitive, this construction is intuitive. And in order to avoid some interpretation problems, okay, so this is a picture of the formula here. Yes, we've got systematic hazard rates for various names and idiosyncratic ones. And okay, in order to avoid problems that arise in the case of Gaussian copula and other copulae as well, that in the situation of co-monotonic defaults, the first default determines the following ones. What is marking? But we may relatively easy replace the co-monotonic case when the next defaults consist of independent increases. So that's a mathematical construction. So just maybe you just have a look at transparencies, but this gives us, leads us to a construction of a Markov process. So we may apply all the theory of Markov chains in calculation, what is useful. So I think applied mathematicians try to tend to an existing theory. And when they don't succeed with that, they create a new theory. But normally we are lazy. What does this picture mean? Okay, I know. So it is a construction of the how in this model defaults look like. So entities default in clusters. So when we deal with systematic default, so bigger, smaller one, or quite big, and of course idiosyncratic. Idiosyncratic default is independent. So this is that's probably the way how we should look at the defaults of various entities in the economy. So either we've got a larger collapse that big number of companies default for say general economic reason caused by the whole economy, all companies just default for their own reasons. I think that's intuitive. Okay, so when we sometimes, so in particular in the case of CDOs, important thing is the default counting process. or for a bank. So for a bank, it is important how many credits default in a short period of time. So when there are few, everything is under control. But when we've got a cascade of defaults, something bad happens. So we would like to construct the some counting default process and try to have a closed formula. So in the case of Gaussian copula, we don't have. We've got efficient numerical methods, but closed formulae don't exist. For this Marshall-Olkin approach, it may be done. So M is the number of systematic defaults, N, number of all defaults. Nj is the number of defaults up to time t, provided the cluster of size I already defaulted. So we've got such a simple formula that probability of M defaults is given that by that formula. So when number of systematic defaults is equal J, and number of idiosyncratic defaults outside the cluster of size J is equal M minus J. So this is still simple algebra. So we've got that formula. And for calculation of defaults of the size for the process Nj minus N, N is, we've got Bernoulli algorithm, so which is relatively simple. Again, simple algebraic formula. So we don't have a closed formula, but we are very, very close to closed formula. What next? And next is the question that was asked, say, some 20 minutes back. Probably you should remember it. How to deal with correlated defaults when we deal with not just positive random variables, but stopping times. So every tau I is not just positive random variable, but is measurable to the filtration. So what does it mean in terms of hazard rates? So for random stopping times, hazard rates are random processes. So lambda idio is a random process. The same with lambda systematic. And the construction so what does it mean that lambda idio and d, no, this is v, and v are hazard rates for the stopping times y and u. That these processes are martingales. And that may be extended to a kind of Malyaven calculus for jump processes. So who did it? Who did Malyaven calculus for jump processes? Okay, I don't remember. So it's going beyond martingales, but that's not important. We are here. So that looks a bit like Malyaven derivative of a positive random variable. No? Okay, irrelevant. Okay, and then of course the stopping times are defined as minimum of idiosyncratic and systematic. And we've got that situation that that term is a martingale. So this is a hazard rate for the stopping time tau. There are no closed formulae, even for relatively simple stochastic processes lambda, systematic and idiosyncratic. And I may probably surprise you, but there is no other attempt to construct correlation for stopping times. Or at least I don't know it. Pity. So I don't know who asked this question. So are you happy? I don't hear. Okay, so these products, or maybe after the break, CDO's pricing after the break. These products were important. They destroyed economy. Misuse of CDOs almost destroyed economy. I would say, so I have to tell you a few words about it, but now probably I will listen to some comments or try to answer some questions. Guys, comments, questions, or you're completely lost?
No, I think they are here. Please. Thanks.
Okay, so let's continue the very last hour of our training course. So I will say few words on CDOs because they are not as important as they used to be, but say literacy requires knowing something about CDOs. What are CDOs? That's called collateral debt obligations, whatever it means. But there are products consisting of various loans which were put into one pool and then divided into tranches. And the tranches, and then some bonds were sold based on these tranches. the construction was that the default was in a pyramid or waterfall. So probably waterfall is the more proper word. Then first defaulted equity tranche, then mezzanine tranche, and finally senior tranche. So, and these products were strongly exposed to correlation. Why? When imagine all the defaults are independent. So that may be relatively easily calculated that equity defaults for sure, almost immediately. Then there is some kind of loss of nominal of mezzanine, but senior tranches are certain investments. Triple A, we would add more A's to that. Probability of default of senior tranches is practically null. But the more correlations we've got in the market, there is more probability of default of senior tranches. And how the word this looks like these days. So maybe you can hardly believe it, but there is too much money in the world. I don't mean your pockets, in general. It's called over liquidity. So all the pensioners, investors, and so on look for opportunities to invest. So these senior tranches seemed to be perfect investment because their coupons were larger than government bonds, and probability of default was calculated by clever guys that is practically null. So it appeared that these clever guys were not so clever. So how it is constructed in mathematical terms. So survival amount associated to a tranche with from the level little k to capital K is defined by this formula. So on the picture, this is exactly that part of default. So either higher or lower. And CDO swaps were priced the standard way, exactly the same way as CDS tranches on the very first slide here. Yeah. So they were considered exactly the same way as CDS. And of course, we've got some tools to price these products. Gaussian copula, Marshall-Olkin copula, some others. So the market model here was really implemented in my company. So we did it for pricing and okay, made some money, especially on the crisis, but that was my last money in the company after the market collapsed. And now a question. I didn't ask too many questions today. Let me ask you a question. What's the reason of the big crisis of 2008? Anyone's got an idea? Nobody. Probably you're right. But the reasons, in my view, was that Gaussian copula is a very simple tool. And CDOs were not that simple. So they were built of loans, especially mortgages, but also with all that big mixing in creating CDOs, some, especially mezzanine tranches, remained. So they were investors interested in senior tranches, which were certain, so say, for pensioners, and equity tranches, which were just very, very random, very volatile, so for speculators. And mezzanine tranches were neither for investors nor for speculators, so it was tough to sell them. So what did the investment banks do? They behaved exactly like a cook. So they put it back to the foot. So were constructed product called CDO squares. And if you look in the market model transition of the risk in such products, you will see that risk, that's not possible to see it with Gaussian copula, but with the market model, yes. The risk moves from equity tranches toward super senior, towards senior. And in fact, the tranches stopped to have sense because risk of all tranches was more or less equal. And it did collapse. And you know what happened. So to make complete the presentation complete, I should mention that for the models of credit risk, there is also one class of models called top-down. So here, so far, we did model individual names and then constructed from that portfolios. Top-down model is we construct the stochastic process representing number of defaults in the portfolio, and then from that we try to extract something about individual names or not. So I would like to finish that part with a theorem that if hazard rates for consecutive default times in the portfolio here defined is form a monotonic sequence, then for every there exists a Markov point process such that the default times number of defaults got exactly this distribution, and the proof is relatively easy. So I think there is no sense to talk about it. You just might have a look how it looks. And this is the moment when we finished our mathematical part of the course. So please ask questions. In a few minutes, I will try to tell you something on the life of a mathematician in a bank. So questions, please. Maybe even to previous parts. Nothing. Okay, so what is quantitative finance? Not in academic terms, but in practical terms. So, what a quant does. So, one function of a quant is pricing of securities. So these days, there are options, swaps. So swaps are very simple product, but very liquid. Before the crisis, we had very complex products, and I think very with poetic names. For instance, 3 colors rainbow options. These days, the number of options is much smaller. So there are, of course, European options, American, Asian options. So as you probably remember, on average, some binary, and that's maybe not everything, but most of it. And question to the audience, why? Why the diversity of options is reduced after the crisis? And I will wait for an answer. What happened? Okay. Yep.
Let me read because investors are risk averse.
Yeah, yes. Investors are risk averse. That's the only answer. So to some extent, maybe investors are more risk averse, but they are first of all are more clever. So trading, when we trade options, what actually we trade? Next question to the audience. Okay, I will answer that question. We trade volatility. So volatility, simple products are exposed to volatility exactly the same way as binary options and all other all the complex stuff. So trading some barrier options are still traded. But trading some accumulators, two colors rainbows, and all that stuff was to some extent cheating, because that was selling or buying volatility from clients, but hiding the margin in complex structure of options, so that as was that happened in Poland 12 years ago. We didn't have much exposure to CDOs, so banks and investment funds didn't lose much money on CDOs, but they lost a lot of money on complex option structures. And complexity is too often used to hide the margin. So simplicity just gives the economic reason as well, selling or buying volatility. Next, calculation of sensitivities. Why calculate? So that's, I think, the main reasons why quants exist. Because maybe this day it is not like that, but say 20 years back, we were hated. David, are you hated in your company? So maybe it's an exaggeration to say hated, but a quant is not someone from outside. It's an implant in a bank. So because businessmen think differently than mathematicians, so they would like to get rid of us if they could, but they can't. Why calculation of sensitivities is so important? And of course, you know why it cannot be done without models. Yes, because sensitivity is a derivative. So when we don't have any functions, we don't have derivatives. We must have a function to calculate derivative. And sensitivities are necessary for hedging. If we had something reduce risk, so we must know the fraction between one asset and the other and how risk is transferred between them. So the exact fraction. So sensitivities are very important. And the second reasons are limits set quite often in terms of sensitivities. Then calculation of risk indicators, all the value at risk, expected shortfall, and so on. So that's required by regulators. So banks, even if they don't want to calculate it, they have to. CVA, for instance. So risk departments are big these days and hire many mathematicians. So probably I think it's the first place for employing mathematicians. So risk departments of banks. And those of you who will be lucky enough will go to trading, to banks or rather hedge funds these days. And say quant trader decides trading policies to be executed by someone else or by himself or herself. So that's a dream of many people. I don't know if it is the best quant life. Quant, of course, why this specialist is called quant, because in English language, words are very close, very short. So quantitative analyst is a bit too lengthy. So what is the synthetic description of quantitative finance? So this is practically activity with all consequences. So a beautiful theorem, a deep result is worthless unless until implemented. It must be something that a trader presses a button and gets a number. And this is a result. Formula is not a result. So that is something we should remember working for a financial company. But there is another side of that. So far, I did try to discourage you to become a quant. But on the other hand, there is practically all stochastic analysis, including Mariavan calculus, Levy processes, fractional Brownian motion, anything you may guess will find practical applications. Sometimes, quite often, even before publication of the paper, because okay, now with the public access, papers are published faster, but Elisa, what's your longest waiting for publication of your paper from submission?
Oh, Dariusz, I think more than 3 years.
So in my case, this is 7 years. But okay, it was not the first journal, but it was rejected in one, in the second.
In the same journal, 3 years.
Yeah, so it's
more than 3 years, because I'm still waiting.
So that's the situation. So 3 years definitely is a time to implement the most sophisticated trick. And there is, I'm saying that with complete responsibility. There is no other practical discipline so close to mathematics. So, and okay, it depends on your temper, of course. So you are happy seeing your results on paper, or you're like it seeing them working. I did a lot of consulting in various in various other fields. And definitely banking is the most mathematical human activity. And what is the contribution of quantitative finance to mathematics or to applied mathematics? Sophisticated numerical methods, quite often linked to Monte Carlo, because Monte Carlo, when we model stochastic phenomena, is natural way of calculating something. So I didn't see American Monte Carlo elsewhere. So it comes from finance, for sure. But other numerical methods like, I think you had a training course on numerical methods, are also finance contributed to development of this field. But since I've written it, this is practical activities very close to mathematics, but not mathematics. So it's not about writing papers. Important results are quite often unpublished. I've heard about it many times that an academician invents something that finds excited. So it's a good paper full of interesting results, and it gets rejected and rejected and rejected in various journals because it was already known. But nobody cared about publishing. So results are not evaluated the academic way. And I don't know about your academic mathematical education. Mine was experimental, so that was the Bourbaki way. I've heard about Banach space on the first lecture of analysis. So was no analysis one. We started with functional analysis. Everything was designed to make us little geniuses. So I don't know if they did. But financial mathematics is against Bourbaki. It's back to analysis one. Concrete calculations are much more valued than general ideas. So for instance, there are no inequalities, there are only equations. Inequality is worthless from a practical point of view. Any research without a numerical example is useless. So it's what I've already said, and results must be described in plain English. So our bosses are rarely mathematicians. I would say they are never mathematicians. So that's a proof that we are still implants. Yes, because various people get promoted, not only from sales, but from risk, from some reporting. You are hired as a young man in a bank and you get promoted and you get to the management board, maybe get the, yes, but practically never head of a quant team is a quant. We are not trusted. So But of course, everybody is intelligent, because making money is for intelligent people. So results must be described in plain English, or plain Spanish, but rather English, because this is even in Spain, because this is an international activity. So what is unpleasant in working in a bank? So promotion principles are different from academia. We get in academia promoted according, say, to quality and quantity of our publications, teaching, and all that university activity. In banks, I've noticed that several times people who would never be promoted in academia are becoming bosses very quickly, because the quality criterion is different. Another issue. The problem must be solved in the assumed time. Must be, because there is not only your problem, but the problem of the whole company. So what in mathematics we do, we can't solve a problem. We don't solve it, or we give a partial answer. I don't know. So, but we are honest. When we don't know the answer, we don't give it. In bank, an answer must be given at any price. So when you can't give the correct answer, you are giving the wrong one, yes? And that's happened too often. So the Gaussian, infamous Gaussian copula is one of many examples. And working conditions. So we like our desk computers, pencils, and so on. And do we like traders shouting over our heads? So you must be able to work in such conditions. And one thing, intellectual property is not protected. So your results belong to your boss. Okay, so the sins of the bank, but everybody is sinful. Academicians as well. So, do you know the model Sabre? Yes, it's one of most popular models. And here is the story by Patrick Hagan on publication of that model. So it was so painful for him that he shared his opinion with everybody. So that was, he's made several attempts to publish the paper in the so-called top-notch journals, and he was molested about sigma algebras and measures and so on. And even as a mathematician, Pat was a modeler. So a guy not caring about rigor. So that was the style of mathematics, the British, not French. And he finally published that in Wilmot, but the model is still very popular. So I had a dream.
We have a question, Dariusz. But okay, the results presented in quant conference, have they already been implemented in the quant libraries a long time ago?
Sometimes yes, sometimes not. Sometimes yes and not. That's because, you know, we mathematicians lie relatively little, but within a bank, lying is quite popular. It's the fundamental tool of work. So I remember when we published the BGM paper, I've heard from many people, but it was implemented many times so far. Was of course not true, because what they say it's already implemented, something else, something similar is implemented, but not exactly what they tell you they've implemented. But on the other hand, that may be true, because not everyone publishes. So, okay, to my dream. I had a dream that practitioners and academicians, because probably it's about my own integrity, because I'm cut in half and would like to be still complete. Practitioners and academicians don't understand one another, and they should. So that's not surprising, because, say, in control theory, so people who construct control devices don't understand those who speak about optimal control of stochastic processes and so on. So for other communities, probably it's not to be saved, but in our community, it is, I think, still possible to have consistency of thinking. So there is a lot to do for mathematicians, but we should, problems like Poincaré said, le problème qui se pose, not le problème qu'on se pose, the problems that form themselves, not the problems that you create for yourself. And okay, so that was everything what I had to tell you. We'll skip tie knots. Nobody wears ties these days, so you don't need this theory. So thank you very much, the organizers, for the possibility to talk to you.